Hello everyone, let me introduce myself. I am Facundo Carballo and today I will explain you all about concurrency problems in Golang. We will see deadlocks, race conditions and starvation problems here in this video. Before we start with the video, I want to mention two things. First, all the code that you will see here, you will have it on my GitHub repo. The link to that repo will be on the description of the video. So I invite you to see the code while you are seeing this video because it will help you to understand better all the things that I am explaining here. And second, if you like this kind of videos, please hit the like button and subscribe to my channel because that will help me a lot to grow up on YouTube. So now I will let you with the video. Race conditions are generated where multiple coroutines, multiple concurrent processes are accessing to the same resource at the same time. So for example here, like we see on the mutex example and also on the atomic example, the only goal of these two coroutines is read the value of this variable and then increment it by 1. But these two coroutines are working concurrently. So here, if we don't apply synchronization mechanisms properly, we can invoke a race conditions between these two coroutines. For example, in this timeline, you will see this easily because the coroutine number 1, in this case, executes first and, well, this coroutine starts to execute. The first thing that this coroutine do is, well, read the value of this variable. Once this coroutine reads the value of the variable, then the coroutine will have to increment the value by 1. But at this point, the operating system quit that coroutine and put the coroutine number 2 to execute. The coroutine number 2 start to executing and, well, the first thing that this coroutine do is read the value of this variable. And, well, at this point, like this coroutine, this first coroutine doesn't increment the value of this variable, well, at this point, have 0 as value, have the same value that have here. So the coroutine number 2 reads the value of this variable on 0. Then, like this coroutine is still executing, this coroutine will increment the value of this variable by 1. So at this moment, if we read the value of this balance variable, we will see that the value of this variable is 1. Okay. But when this coroutine number 2 ends, comes again the coroutine number 1 to execute. But like this coroutine, the only thing that have to do is increment the value of this variable that this coroutine already read the value. So here, the coroutine number 1, the only thing that will do is increment the value of this variable from 0, because 0 is the value that this coroutine reads here, from 0 to 1, because this coroutine increment the value of this variable by 1. So we'll go from 0 to 1, instead of what we expect, that is, at this point, this variable has a value of 1, so here, when this other coroutine increment the value by 1, 2, we'll go from 1 to 2. That is what we expect. But like here, there is a race condition. In some cases, the results of our programs will be different from that we expect, although the code is correctly. So because of that, we have to implement synchronization mechanisms properly. So now I will show you an example of this race condition on code. So here we have two functions, a race condition function and a do work function. This race condition function, what it does is execute 10 coroutines and all of those coroutines will do this do work function. This do work function, the only thing that does is increment this resource variable by 1. So if we execute here 10 coroutines and all of it wants to increment this resource variable by 1, at the end, when all of these coroutines ends, we expect that this resource variable have a value of 10 because there are 10 coroutines trying to increment this resource variable by 1. But we will see here like we are not applying any synchronization mechanism here to increment this resource variable, and this resource variable is accessing by a lot of coroutines in a concurrent way. We are provoking here race conditions. So it will be some cases where this resource variable will not be equal to 10. It's the same example that we see before on the mutex and the atomic implementation. But here, like we are explaining race conditions, I have to repeat this example because remind that mutex and atomic synchronization mechanisms are here to prevent these race conditions. So here this function, this race condition function, will execute this for end loop until gets a balance different from 10. When this function gets a value on this resource variable different from 10, we'll execute this part of the code and we'll finish because we'll break this for end loop. So to show you this, I will execute this function so you can see that it will be one case when this resource variable will have a value different from 10. And here is. We have it here, a balance of 9 when we expect a balance of 10. Other concurrency problem is deadlock. Deadlocks are generated when two or more coroutines are trying to access to the same critical zone using mutex as their synchronization mechanism, but using that mutex in a bad way, like you can see here on this diagram. Here we have the coroutine number 1 and the coroutine number 2. Both of them wants to access to this value variable. It's an example very similar to this, because we have two coroutines that wants to get access to some resource, to some variable. And well, here we have these two coroutines that wants to get access to this resource, this value, but like we want to prevent race conditions, this other concurrency issue, well, here we apply mutex, a synchronization mechanism to prevent those race conditions when these two coroutines trying to get access to this particular resource. So to prevent that, we use mutex. But here we are applying mutex in a bad way, because this coroutine number 1 lock the mutex A first and then lock the mutex B, while this other coroutine first lock the mutex B and then lock the mutex A. When we have this situation where two or more coroutines are trying to get access to the same resource but with different order in their mutex, here we have a very clear situation of a deadlock. Because imagine this situation like you can see here on the timeline. The coroutine number 1 executes first. So this coroutine, the first thing that we'll do is lock the mutex A. Then, for any reason, the operating system quick that coroutine and put the coroutine number 2 to execute. The first thing that this coroutine number 2 will do is lock the mutex B, and can lock the mutex B because there is no other coroutine locking the mutex B. So can lock the mutex B. The operating system quick the coroutine number 2 and put again the coroutine number 1 to execute. So the coroutine number 1 gets here, so left to lock the mutex B. And when the coroutine number 1 will try to lock the mutex B, the operating system will tell to the coroutine 1, wait, because the coroutine number 2 already have locked the mutex B. So you have to wait until the coroutine number 2 ends. Okay, the coroutine number 1 gets here blocked until the coroutine number 2 finish. But what happened? Here the operating system quick the coroutine number 1 because it's blocked and put the coroutine number 2 to execute. And well, when the coroutine number 2 start to execute, the coroutine number 2 will start here because the coroutine number 2 already locked the mutex B. So the only thing that have to do now is lock the mutex A. And when this coroutine try to lock the mutex A, the operating system will tell to us, as a coroutine number 2, hey, you have to wait here because the mutex A is already blocked by the coroutine number 1. So you have to wait until the coroutine number 1 ends. Okay, but the coroutine number 1 also it's waiting. And why this coroutine is waiting? This coroutine is waiting because this coroutine needs something that have the coroutine number 2, and the coroutine number 2 is waiting too because the coroutine number 1 have something that this coroutine needs. So here it's a clear, simple situation of deadlock where two coroutines are provoke a simple deadlock. And that's it only because we use in a bad order the mutex. If we use the mutex A first here, if that was the case, the coroutine number 1 can execute completely and then the coroutine number 2 will execute completely again. But like we use this particular order of locking this mutex, we are producing a deadlock. So now we will see this example on code. So here we have three functions: a coroutine A, a coroutine B, and a deadlock function. This deadlock function, what it does is generate two coroutines, a coroutine A and a coroutine B, and then wait until these two coroutines ends. But what's happened? If we are provoking a deadlock, these two coroutines will never end. So what this coroutine A and this coroutine B does? Well, it's the same that we see here on the diagram. The coroutine A will lock the mutex A first and then lock the mutex B, and the coroutine B will lock the mutex B first and then lock the mutex A. In some point, when these two coroutines execute this first line and try to execute this second line, will generate a deadlock. So when our program gets inside of a deadlock, it will exit immediately, so our program will finish. Because if our program will not finish, our program will be waiting forever. So now I will show you this to see what happens when we have a deadlock. So I will execute this deadlock function to see what happens. And well, here we have the deadlock. It's like an error, but our code, if we don't know what is happened, we see our code and we think it's okay. But the only thing that we have to change here to prevent this deadlock is change the order of the mutex A and the mutex B in one of these two functions, because we have to do the mutex lock in the same order always. So I will lock the mutex A first and the mutex B then. So here I have to make that. And for the unlock, I recommend that always follow the same order. So here we have to unlock first the mutex A and then the mutex B. When we use mutex, we have to be sure that we use it in the correct order always. Because if we don't follow the order in some cases, we can provoke a deadlock, and we don't want that. So if I fix only the mutex order and try to execute again, you will see that we'll execute correctly. So here we can see that the function ends correctly with a resource A value of 2 and also with a resource B value of 2. And that's because, well, our coroutines, each one increment the resource A by 1 and then increment the resource A by 1 and the resource B. So this resource value was incremented twice by 1. So when the function ends, we expect that these two resource values gets on 2. So it's fine. So the last concurrency problem that we will see is starvation. Starvation, when occurs? Well, starvation occurs in situation like this that you can see here on this diagram, where we have two coroutines that are looking to get for a particular resource, a particular variable, and to avoid race conditions, use mutex to synchronize the access of that coroutines to that particular resource. But how starvation occurs? Well, occurs when a coroutine or a concurrent process cannot access never to that particular resource. Occurs when a coroutine, a concurrent process, gets blocked forever in the mutex. And that's when happen. Well, happen when a coroutine get access to that particular resource, but will never unlock the mutex of that particular resource. Like you can see here, this coroutine number 1 access first to this mutex, so it's the first coroutine to get access here, and well, the mutex allow to this coroutine to access to this value, but this coroutine never unlock the mutex, never. So it will use this value forever until the main program ends. So this other coroutine, when try to lock the mutex A, the operating system will tell to the coroutine number 2, wait here, because the coroutine number 1 already have the mutex A locked for the coroutine number 1, so you have to wait here until the coroutine number 1 ends. But what happens? The coroutine number 1 never ends, so this coroutine will never execute, will never finish, because it will be waiting forever. So that's what happens. That is starvation. So we will see this on code now. So for this case, we have here two functions, a coroutine C and a function of starvation. Here we have a global mutex and a global value variable that is initialized on 0. The starvation function, who is the function that we will execute here, this function, the first thing that does is lock the mutex, this global mutex, and then execute this coroutine C in background in a concurrent way. And then, while this coroutine C is executing or not, this function of starvation creates a for end loop that will never end, and this for end loop will print starvation every 3 seconds, because here is waiting 3 seconds, and then will print again starvation and so on. And what does this coroutine C? Well, this coroutine C will try to lock the mutex, the global mutex, but will never can, because this starvation function, the first thing that does before to execute this coroutine C is lock the mutex, but never unlock the mutex. So here we have an starvation example because this coroutine C will never execute. So if I execute this starvation function, you will never see this message of coroutine C value plus plus. The only message that we will see on the console is starvation. So I will execute this to see what happens. And here we are seeing our first starvation, our second starvation, and well, we can be waiting here forever because the coroutine C will never execute. And that's because the starvation. So to prevent that, we have to always lock the mutex and unlock the mutex. And this process of lock and unlock will not have to be outside of a for end loop, because we can use mutex in a for end loop, but the mutex have to be inside of the for end loop, because if we lock the mutex here and then we go inside of a for end, yes, we are locking the mutex correctly here, but we will never end this for end loop. So if we want to prevent, for example, the print on the console, we have to do this instead. We have to here inside of the for loop lock the mutex and then unlock the mutex. If we apply this, the coroutine C will execute correctly without problems, because the starvation function will lock and unlock the mutex inside of this for end loop. So every time that this for end loop executes, we'll try to lock, and when this function can lock the mutex, well, we'll print this, we'll wait for 3 seconds, and then we'll unlock the mutex. So in that particular case, when we unlock the mutex, we are allowing to other coroutines that can use this mutex too to enter to this critical zone and do wherever these other functions wants to do. So we will check this to show you that using this, the coroutine C will execute properly. So I execute this, and here the coroutine C executes. Like I always said, with concurrency, we don't have the control of our program, because we can think that the coroutine C, like is here, it will execute first that this, but you can see here that was executed twice, this for end loop, and then the coroutine C. So when we work with concurrency, we don't have the control of our programs. The order of our programs depends on the operating system now. But that's fine, because concurrency improves the performance of our programs. But like always I said, we have to be careful with concurrency, because applying bad practice in concurrency, it's dangerous. It's very dangerous for our programs. So that's all. That's all for starvations. And well, that's all for this video. I hope that you could understand all about it. I will ask you again that if you like these kind of videos, please hit the like button and subscribe to my channel, because that will help me a lot. And another thing, if you have any doubts about this video or wherever, let me know that here on the comment section. You can leave me a comment and I will respond you quickly. So now, see you on the next video.